Okay, so in lectures 8 and 9 this week on visualizing data, we're going to learn about why we need data visualization and why it's always the first step in any type of analysis. We're going to talk about different types of tables and types of graphs, and you should know the differences and you should know what each type can be used for. We're going to learn about the principles of effective data visualization and how to critique graphs and how to recognize what features of a graph can help a reader understand what's going on and what features can hinder that process. In addition to the two pre-recorded lecture videos, I'm also going to post a video showing you how to make some simple graphs in Excel and Google Sheets, and that will be something that you'll need to do on the homework this week. Okay, so the topic is visualizing data. I want to start with some data visualization pioneers from history, Florence Nightingale and John Snow. And I'll start with the story of John Snow. Not this one, this one. Maybe you have already heard of John Snow before. John Snow was a doctor in the mid-1800s in London. And London at that time was a filthy place. The city was growing rapidly. There were huge, dense populations, but neighborhoods in many places didn't have sewers. People stored their sewage in their basements in rooms that were called cesspits. And there were people whose job it was to go around and empty the cesspits in the middle of the night. And these cesspits overflowed and they leaked into the water system. And so there was a lot of disease. These are some of these nightmen. That's a very good way to spread things like cholera, the bacterial disease or disease caused by the bacteria shown here. Cholera was killing a lot of people in that time, but nobody knew at that time where it came from. The most popular hypothesis was that cholera was spread through bad vapors in the air, and that was called the miasma theory. John Snow, the doctor, had been skeptical of the miasma theory for a long time, but he had no proof. Well, in 1854, London had one of the worst outbreaks of cholera ever. Over 500 people died within a few weeks in just one neighborhood of the city, Soho. And when this 1854 epidemic struck, John Snow started going door to door, talking to people, gathering data. He wanted to know who died, where they lived, and as he started to record this information, a pattern became apparent. And this was the map that he drew. These dark blocks on this map are patterns of where deaths happen. All of these deaths were clustered in a fairly tight area. Not only that, John Snow realized that they were clustered around a particular water pump, the Broad Street water pump. And this is where people got their water back then. This is a modern version of his map, and so you can see it a bit more clearly. The red dots here are the deaths, and the blue shapes here are the water pumps. The star is the Broad Street pump, the center of this cholera outbreak. So he noted that for all of these deaths, nearly all of them, the Broad Street pump was the closest pump to the place where the person had lived. And in some cases, there are people who had worked near the pump or gone to school near the pump. So he found evidence of a really strong connection between this particular pump and the outbreak of cholera. What's more, he found a gap. There was a place right next to the pump where there should have been a lot of cholera, but there wasn't. And so he went there to talk to people, and he found that it was a monastery, and the monks that lived there only drank home-brewed beer. They didn't drink the water. So it just provided further support to his hypothesis that cholera was a waterborne disease and it was spread through the sewer system. And so this is remarkable. This is a data visualization in the 1800s that kick-started the whole field of epidemiology. So today, the original Broad Street water pump is gone. And if you go there now, there's a pub called the John Snow Pub, and there's a replica pump erected in his honor. And you can, maybe when travel becomes more and more possible, you can go there and you can do a pub crawl visiting some of the same sites that John Snow visited. Okay, the other person I wanted to tell you about is Florence Nightingale. She was a social reformer, a statistician, and she was the founder of modern nursing. And she came to prominence while serving as a trainer for other nurses during the Crimean War. She organized care for lots and lots of wounded soldiers. And she kept really meticulous data. She organized data on how soldiers were dying, on causes of death. And she invented this remarkable graph. This was like the mid 1800s again, and she created this visualization. No one had ever done this before. It was called at the time a coxcomb, but it's essentially a kind of a bar graph showing the distributions of causes of death. In this case, the different segments around the radius of this image represent different months of the year during the war. And so what you can see right away is that the grayish areas of her graph, which are deaths from preventable infections and diseases, are by far the biggest burden. And so by tabulating the data, by presenting it graphically, Florence Nightingale showed that deaths from infections far outnumbered deaths, like direct deaths during the war from being killed directly during the war. And so this really emphasized how important cleanliness and hygiene was in hospitals to people's health and survival. And so her invention here was the basis of today's histograms, bar graphs, and many other kinds of plots. You can read more about Florence Nightingale at this link here. Okay, so I tell you these examples because they're really nice examples of how visualizations can provide really important insights. If we fast forward to today, graphs are everywhere. You can't read a news story about COVID without looking at some kind of data graph. So good visualizations can give us good insights. Some visualizations are nice looking without providing much insight. And the worst ones just confuse us without conveying anything. And so that's going to be a topic this week. In this lecture, we're going to learn about different types of data visualization. In the next lecture, we'll talk about what makes a good visualization. So I use visualization to refer to methods of displaying data in general. It includes tables and it includes graphs. So tables are data visualizations too. They are, so two key points on this slide. The first one is that visualization is the first step to understanding a data set, including your own data. So it's not just for communicating it to others, it's also for making sense of it yourself. Okay, so a visualization is the first step to any analysis. The other key point I want to make here is that visualizations are not some kind of objective science. When you're making a graph, there's a lot of decisions that go into making it. And we're going to talk more about that. These decisions affect what the viewer takes away and how easy it is for the viewer to visually make sense of the information. And so that's going to be a big topic of the next lecture. I also mentioned infographic on here. Infographics are just kind of posters or displays that combine a bunch of visualizations into one story, I guess. Okay, so the purpose of good visualizations is to make it easy for the viewer to interpret the data correctly. In other words, to quickly see what's going on with the data. And so I want to show you a quick example that illustrates why looking at the data is always the first step to any analysis. And in this example, suppose that you're interested in the relationship between two numerical variables, variable x and variable y. So that's the scenario. And I've got 4 different data sets. Okay, so we've got 4 different sets. All of them have the same sample size. I think there's like 10 or 12 data points here. And we have an x and a y in each case. And the 4 data sets all have some of the same properties. The mean of x and the mean of y are the same in each data set. The standard deviation of x is the same in each data set. The standard deviation of y is the same. And the correlation coefficient, something we haven't covered yet, but we'll do later on. But if you look at the correlation between x and y, you get the same statistics in each of these 4 data sets. So if you just look at these numbers, these 4 data sets look very much the same. However, this is what these data sets look like when we plot them. So we've got data set 1, 2, 3, and 4. And I hope you can see that we've got very different things going on in each of these 4 scenarios, and that a linear relationship between these 2 variables is not necessarily appropriate in each case. So what's plotted here is each of the 4 data sets, and then the blue line is the linear best fit statistical relationship between X and Y if you just run that relationship without any alterations. And so the blue line is a good indication for data set number 1. But in data set number 2, I hope you can see that a straight line is not really an accurate description of the relationship or the function of how Y depends on X. And in data set number 3, we've got a very tidy relationship among most of the data points, but then there's this one data point that lies outside of that relationship. It's an outlier. And so that outlier is really influencing the straight line fit of that model, and something that we need to look at the data to consider whether we want that data point to be informing that model. And then in data set number 4, we have the exact X and Y have no relationship in the majority of data points, and then there's a single outlier in X and Y that's totally driving this relationship. So I just wanted to show this example to you to show that if we didn't look at the data, we'd come to the same conclusion about this relationship in all these 4 data sets, but it's not the real relationship that's underlying what's going on in 3 of these cases. Okay. So these graphs can reveal patterns that just numbers in a spreadsheet cannot. For example, outliers. Okay, so it's important to make visualizations not just for the reader, but also for yourself to understand your own data. All right, so we're going to get now into the types of data visualization that you're expected to learn in this course. And we'll start with types of tables. Okay, so a table, it's kind of funny to think of it as a visualization because it's not very visually appealing. But a table is just a data structure that organizes information into rows and columns. So instead of just showing someone your entire data set, might not even fit on a page, a table is a way of summarizing, presenting a numerical summary in rows and columns. We're going to look at 3 types of tables in this course. A summary table, I'd say, is the most common type when you read scientific papers. It just summarizes descriptive statistics, or it summarizes the results of a statistical analysis. A frequency table is a very simple type of table, and it just shows you the counts of different categories within a categorical variable. So a frequency table takes a single categorical variable and just shows you its distribution. A contingency table is when you look at the relationship between 2 categorical variables, and it shows you the counts of membership for these 2 categorical variables and all possible characteristics that an individual can have. So I'm going to show you examples of these 3 below. So here's an example of a summary table. This is one from a study of human height across different regions of Poland, about 120 years ago. So we've got columns here like sample size, we've got different regions of Poland, sample size, we've got people's average heights, we've got descriptive statistics, we've got standard deviations. So that's a summary table. Okay, here is a frequency table. This is data from you, students in our class. When I polled you at the beginning of the term, one of the questions I asked was, what year of study are you? So that's a single categorical variable, right? You could have responded. There were actually more response categories in this, but I've collapsed 3rd year and 4th year into one category for the purpose of this frequency table, just to make it fit. And so we've got students that could be in the 1st year category, the 2nd year category, the 3rd year category, and then we've just got counts or frequencies, number of students in those categories. So that's a frequency table. Okay, now I'm going to show you a contingency table. So this is data from our poll, that same poll at the beginning of the term. And now I'm showing you the relationship between 2 categorical variables, a student's year of study and the grade they expect to get. So I've got each cell of the table represents how many students were there in that set of characteristics, right? So among the 1st year students, we can look across the top row. We've got 81 students who expected to get an A or better, and we've got 26 students who expected to get something lower than an A. So I just took that variable, your answers in the poll, and I created a categorical variable from it, whether or not a student expected to get at least an A. And then we can look down to the next row and the next row, and you can see the counts of the students in second year. 4 of them expected a B or lower, but 22 of them expected an A or higher, and so on. Okay, and just to show you, here's what the spreadsheet would look like for the two variables that went into this contingency table. So we've got 2 columns, each of which is a categorical variable, right? So each row is a student, and each student responded on what year they were in, and you actually responded with numbers, but I converted the numerical response to a categorical variable for the purpose of this visualization. And there would, of course, be more rows below. Okay, so that is a contingency table. It's like a frequency table, but it's like for 2 variables now at once instead of 1. Okay, so here's a little practice question. So given the data in this contingency table on the left, how many rows would there be in the spreadsheet? So how many students were there, right? Because each row is a student. Okay, so now let's get into types of graphs. And then at the end of the lecture, I'll give you a few more practice questions. These are the types of graphs that we're going to touch on. There are many, many more. These are just the ones we'll see in this lecture, and you'll be expected to know about for the course. Okay, so I'm going to organize them by their purpose. And at the end of the lecture, I've got a little summary slide that's a really good study aid. Okay, so first of all, suppose we want to show the distribution of a single numerical variable. We've done that already in this course a bunch. And the way to do that, one way to do that is a histogram. So a histogram uses the area of the rectangular bars to display the distribution of a numerical variable. So this data that I'm showing you in the histogram in this kind of lavender color is from an experiment that I ran with students a couple of years ago, where I asked them to predict how well they were going to do on a memory test, and then I tested them. And so this is the distribution we got of students' predictions. And I said, predict how good your memory is on a scale from 0 to 25. And so you can see how students tended to answer in multiples of 5. We have kind of these peaks at 5, 10, and 15. So this is a multimodal distribution. So in the histogram, the intervals, the widths of these bins is something that the histogram maker can choose, right? So, and it should be chosen carefully because it'll change how the histogram looks. By the way, this red line is my own predicted memory score. I did the test as well, and I thought I was going to do really well. My prediction for my own memory was in the 82nd percentile of this whole distribution. Okay. And actually, I was in the 82nd percentile for confidence, but then when we actually did the memory test, I was pretty poor. I was only in the 16th percentile for memory ability. Okay, so the second histogram here is like the actual scores on the memory test, and the red line is my own. So just reminding you of the definition of percentile here. Okay, so I wanted to show you features of a good histogram. Okay, so the bars have to come down to 0. So histogram is showing you counts on the y-axis, and it should come all the way down to 0 so that the size of the bars visually, kind of the colored area accurately represents the amount. We shouldn't have any separation between the bars, and this helps us reinforce the perception of there being a numerical scale. We should use readable numbers along the x-axis, not, the numbers that are actually stated along the x-axis should be easy to read. And it's helpful to tell the reader what the total sample size is in the caption. Okay, on this slide, I'm showing you 2 columns here, and we've got the same data represented in each column. So we've got 3 histograms showing you predicted scores and 3 histograms showing you actual scores. Same data in each case, but I'm showing you what happens when you change the bin width, right? So as we go down the page, we're using bigger and bigger bins. And you can see how it really changes your perception of the data. When you get down to these really big bins, you totally lose sight of the fact that we've got this multi-peak distribution. So the size of that interval can affect our interpretation as a reader. And so it's important to consider that. Okay, a second type of graph that also shows the distribution of a single numerical variable is a probability density. And a probability density graph is just a smoothed histogram. So instead of having frequency on the y-axis, now we've got probability. So here I'm showing you the exact same distributions that I did before. I've added the mean of the distribution as a black dotted line. It's really too fine to see in the upper left, but it is there on all four of them. And so it's predicted score. We've got the same data on the left-hand column and the same data on the right. And I'm just showing you how this is an alternate way of visualizing the distribution. And I also just wanted to show you that a box plot is another way to represent this. So a box plot is kind of like a condensed way of illustrating a numerical distribution. And we've looked at this example, we've looked at something like this before, where I show you a histogram along with its box plot. We can show the median, that's what's illustrated in the middle of a box plot, the percentiles, and then usually the whiskers of a box plot are drawn at 1.5 times the interquartile range. That's usually the default way that box plot, like software will make box plots. So that's done by the software calculates the interquartile range, and then it calculates what is 1.5 times the interquartile range. That's where we put the outer whiskers. And if there are any data points outside 1.5 times the interquartile range, they get plotted outside those whiskers like this one value does here. All right. So another way to represent distributions of numerical variables is violin plots. And it's just a probability density, a smoothed histogram turned on its side with its mirror image shown. So this type of plot is becoming more and more common. In this particular example, this is some data from the web. It might not even be real data, but in this particular example plot, what we're seeing is violin plots of these three distributions. It is some kind of experiment where something was dosed with a drug, and we had three different dosing regimes, and we can see that whatever this drug did, it made the thing get longer. So, and we've got box plots shown on top of the violin plots in this case, so for even more detail. So it's a combination, a hybrid plot. Okay, so we've covered a bunch of the ways to show a distribution of a numerical variable. What about the distribution of a categorical variable, like COVID vaccine status, or species, or eye color, or something like that? Okay, so here's an example. I've taken a categorical variable from our pre-course survey of what year of your degree are you in. This is what the data look like in the spreadsheet on the top right. And then I've made a frequency table. That's one way to visualize that information. So there were 159 students in this sample, and that's the breakdown of what year they were in. And here I'm showing you first, second, third, and then I've got fourth year or greater as the fourth category. I can also show that distribution using a bar graph. Okay, so a bar graph is a really useful graph to show the distribution of a categorical variable. And so right away, I hope you can see that it's much easier to take in this information from this bar graph than it is from the frequency table. It's faster to see, oh yeah, there's like, by far the most students are in first year, and there's several times more first year students than there are in the other categories. However, if you look at how many non-first year students are, there's still quite a few. Okay, so in a bar graph, the area of these colored rectangles visually corresponds to the frequency, right? So the area of this bar relative, the first year bar's area relative to the second year bar's area the comparison of those areas should match the comparison of those two numbers. Okay, and so here's a little bit of summary on what makes a good bar graph. It's helpful to have the categories along the x-axis, the horizontal axis, match a natural order if there is one. If you go back to the graph on the previous slide, it would be kind of goofy if I had those categories ordered like second, first, fourth, third, something like that. So I've made them match the natural order. Sometimes if they don't have a natural order, for example, if your variable is a nominal variable, it's useful to order them by frequency of occurrence. So putting the most common category first and then less common, less common, less common, or vice versa. And that makes it easier to visually make sense of the bar graph. The bars should be of equal width. And you have to pay close attention to where you draw the baseline for the y-axis. It should be 0, and that ensures that the height and colored area of the bars is proportional to magnitude, and that helps avoid the problem on the next slide. The bars should be of equal width. Okay, so that's just repeating the previous one here. And again, that's for the same reason. We want the area of the colored region to accurately indicate magnitude differences. And the bars should be have some margin or some white space between them. They shouldn't be fused together. And the caption or something on the figure, it's helpful if it provides the total number of observations or the sample size. Okay, so how do we show the relationship between two variables? So moving on now, we're going to look at the relationship first between a categorical and a numerical variable. So one of your variables is categorical, one is numerical. Okay, so I want to give you a little bit of background information about the data I'm going to show you. This is this is an experiment. It's data from an experiment I conducted with students in this course. I surveyed the students. I haven't done it this year. I'll conduct a different experiment with you, but I want to show you this study. I surveyed students and I asked them to study a list of 18 words. And then they had to set the list aside and they had to do a test and see how many of the words that you studied could you remember. And about 50 students took part in the test, and took part in the experiment. The test that they did got scored out of 10. Okay, so the students didn't know they were in an experiment, but they were in an experiment. And about half the students saw a nice organized list, like this one on top, where the words they had to memorize were organized topically. And the other half of the students saw a list like this, where the words were randomized. And so the words were grouped with other words that didn't have any relationship to each other in terms of their meaning. And so the question was, would the nice organized list improve the students' ability to memorize? Would it help them recall more of the words? Okay, so they would study the list, so they only saw one, or the other students were randomly put into one of these two treatments, and then they did a short test. And let's look at, did it affect their memory? So we can think of this experiment as looking at the relationship between two variables. We've got the numerical variable, their memory score, that's the outcome, and then we've got the categorical variable of the type of list they saw. That's the thing that we're hypothesizing might influence memory. Okay, and so here's a couple of options for how to graph this information. So these are bar graphs, and on the y-axis, I'm plotting a single mean memory score for each of the groups in the experiment. And on the x-axis is just the categorical variable of which group were the students in. Were they in group 1, the organized list group, or group 2, the students that got the random list? Okay, so I'm using bar graphs again. And I'm plotting a mean, a descriptive statistic for each of the two groups. And that's sometimes done. And so I put it in this part of the lecture because it is often used for this purpose. But I want to warn you, I don't recommend using a bar graph for this purpose. And I'm going to show you why on this slide. If you look at the graphs on the bottom of the slide, there's a difference between the left and the right. And the difference is I've started the x-axis at a different point. So on the left, I've started the x-axis at 5, and on the right, I've started at 0. And so that's a choice that I made making the bar graph. But bar graphs should really start at 0. And do you see how, depending on that choice, it changes my visual perception of the difference between these two groups? So on the left, it looks like there's a bigger difference in the mean scores on the right, that visual difference is smaller. Okay, so which one of these two is a better visual representation of the data? Something to think about, and we can talk about that when we meet on Zoom. Remember, it's an important feature of bar graphs that the visual colored area, or the shaded area here, should correspond to the magnitude of the statistic for each group. Okay, so actually neither of these two graphs are very good, and we can talk about why when we meet on Zoom. I'm going to show you a couple of better ways to represent this relationship between the numerical variable and the categorical variable. The first one is box plots. These are great. They show the median, the quartiles, and they show extreme measurements or the range of the data with these whiskers, depending on the how the box plot is done. And so this is a much better way because we don't just see the bar graphs just show us a single value. Box plots show us more about the distribution, because remember, we've got a whole bunch of students in each of these groups, and now we can see the distribution of their scores. We can see the central tendency, and we can see the spread. Okay, so right away we can see that there's a lot of overlap between these two groups. There's a lot of spread in students' memory scores in this test, but it does look like on average, the students that saw the organized list tended to score a little bit better. So overall, this is a much better visualization because we get more information about the data that went in. Here's another option for representing this information. We can also use a dot plot. The term dot plot has been used for different types of graphs. In this course, I'm going to use it to refer to graphs where we're looking at a numerical variable on one axis and a categorical on the other. Okay, and so each observation, each student is represented as a point. And so we've got the students in this category number 1 and category number 2. I've also done something here because a lot of students, because memory score is discrete, right? The students could only get scores of like 10, 9, 8, 7, 6. There's no decimal score. There's a lot of overlapping data points. So what I did was I used something called jitter, which adds a little bit of random displacement to the data points, and that spreads them out and makes them a little bit easier to see. Because what you don't want is to have data points covering up other data points, because then that means you can't see what the sample size was. So I like this even better than the box plot personally because it shows all of the data. You see even more information here. So that's pointing out the jitter. I've added the median on here with a dotted line, and I've added the mean with a solid black line. The dot plots can have other statistics added on with lines or any other feature you want. Okay, I want to just show something that is similar to a dot plot, but not exactly the same, and that's a dot and whisker plot. And that's when you have values of an estimate as dots, plus or minus some uncertainty or error bars, and those are the whiskers. And so this can be often used to show statistical estimates across different categories, like the example I'm going to show you on the left of the slide. And it's also used in other types of studies, many of which we haven't covered in this course, but we'll see more of them later on. So I just wanted to introduce this as a type of plot now. So here's an example of just made up data. So some drug that's supposed to influence levitation, right? So we've got an estimate for each of our group. Some people got drug A, drug B, some people got control. So maybe this is like, oh, it's the mean score, and then the whiskers there, and then the axis tells us what the whiskers are, that they're standard deviation. And here's another example. This is from a real analysis. These are a bunch of different countries along the vertical axis, and along the horizontal axis, we've got dot and whiskers plotting the organ donation rates. So how many people per million are organ donors? And I think it must, I don't actually know. I'd have to go and look at the study, and it must not be people who signed up to donate organs, because surely that's more than like 10 out of a million. But yeah, you can see that there are differences among these countries, and maybe it's like the rate of with which organs can be used. Okay, so moving on, how do we show the relationship between two categorical variables? Okay, so we've already looked at a way to do that with tables, and that would be with a contingency table. And so that gives you the frequency of occurrence for all possible combinations of two or even more categorical variables. In this course, we'll generally look at contingency tables that are two-dimensional. In this particular contingency table, I'm using data from this course. I'm looking at the relationship between a student's year of study and also their response to the question on whether or not they'd read the course outline yet in the first week of class. And so we've got like year of study is the columns, having read the outline or not is year of study is the rows, having read the outline is the columns. And then I've also added on a row and a column for the totals. And not every contingency table has these totals, but sometimes it's nice to add those on. Okay, so that's a lot of information to take in from a table. This is a graph that shows you the exact same information. So this is a graph that shows you the relationship between two categorical variables. It's called a mosaic plot. It's very similar in concept to the bar graph, except we're using two categories here, or two variables here, right? So we've got multiple colors to represent membership in these different categories. So in this case, we've got our columns are what year different students are in, and we've got black areas representing students that had read the course outline and gray areas that represent students that had not. And so it's much easier to see, I think, from this plot that the majority of students had read the course outline, and that it kind of differed a little bit in the different years, but I don't really see a consistent trend. For whatever reason, second year students and fourth year students were more likely to have read the outline. I'm not sure why third year students were a little bit less likely to have. I can show you the data from last year where there really did seem to be a consistent trend. In last year, it was like the upper year students in the course were much more likely to have read the course outline. So that kind of made sense that they had been through all of this stuff before and they knew what was going on. I don't know why this year was a little bit different. Okay, so coming back to the data from this year, another way to represent the relationship between these two categorical variables is through a grouped bar graph. So it's the same information as in the mosaic plot, but now in bar graph form. And so what we've got is the two different groups represented as our different colored bars. Okay, so again, we can really quickly see most students had read the outline, and most of the students in the class are first year. And it's a bit hard to tell whether the proportion who had read the outline differs across the different years. Okay, what about the relationship between two numerical variables? This is a really common one. One of the more common types of graphs that we'll see is a scatter plot. And so we've got a numerical variable on the x, a numerical variable on the y, and the different individuals in our sample are represented as points. This particular graph is data from one of these memory experiments I did with students in the past. I'm plotting students' actual memory score against their predicted memory score. And what you can see is that, well, there's not really a strong relationship here. I've added a line, a dotted line where y equals x. So any dot that's exactly on that line would indicate a student whose predicted score was exactly the same as their actual score. Mostly what I see here is that students predicted a really wide range of scores for themselves, but they actually tended to do quite well. The average actual scores were quite high. Okay, here's another scatter plot with data from you this fall when I surveyed you in the first week of class. This is showing your expected grade in this course. Oh, there's a typo in my axis label. It should be grade. Expected biology 1105 grade as a percent, plotted against your previous science grade as a percent. And so here you can see, yeah, there's a pretty decent positive relationship. The students who tended to have a higher recent grade tended to predict that they do better in 1105. And again, I've shown the line where y equals x. You could pay attention to things like the range of values along the axis that I've chosen to show. I've chosen to just show grades that were above 50. There weren't any students who expected a low grade, or at least the students who provided a really small number I thought were answering in a different grading system. So I've removed those. And that's also why the sample size here is 97 students, because there were some students who provided a grade in a different format or who provided like a text answer. Okay, so as a general principle, whenever we're graphing the relationship between two variables, we usually want to put the independent variable on the x-axis. Okay, so that's the thing that we expect to cause something else. Or in an experiment, it's the thing that we manipulate, right? If we're giving people a dose of a drug, and we've got different dose categories, if we're manipulating that dose, that's our x variable. That's our horizontal axis variable. We want to put the dependent variable, the effect or the outcome variable, on the y or the vertical axis. So that's a really important rule to keep in mind. It just makes graphs make more sense. Now, that said, we don't always know which variable is the cause and which is the effect, and that's something that we'll talk about next week. Okay, there's a few more types of graphs that I'm going to cover looking at relationships between two variables. One is a line graph. A line graph is when you have dots that are connected by line segments, and it's used to show a trend in a measurement over time. So usually the x-axis in a line graph is time or some other type of ordered series, because it only makes sense to connect the data points if you can put them into some kind of order. And so the example that you're seeing here is real data on the Dow Jones Industrial Average, some kind of economic metric from showing you what that Dow Jones was over the years from the 20s to the mid 1950s. I guess it's the 20s again now, but now it's the 2020s. Okay, so with line graphs, we've got a numerical variable on the y, and then we've got some kind of ordered numerical variable on the x. Okay, so very important. For line graphs, it also has to be true that there should only be one y value for each x, right? If you've got a data set where a certain x variable or an x value could have more than one y, it doesn't make any sense to connect them with lines. You need to have a series where there's a single y for each x. You could have a line graph with multiple series, right? So we could have, a stock market graph where we have a line for the Toronto Stock Exchange, a line for the New York Stock Exchange, and so on. But within any one of those series, there should only be one y for each x. Okay, so there's a really neat website set up by Google where you can explore line graphs, explore data based on people's search activity over time. And so you can go there yourself and play around with it. But you can look at, for example, people's searches for different statistical terms like null hypothesis and p-value, and you can see right away this really interesting pattern. You might have to zoom in to see closely, but people search for null hypothesis in kind of a seasonal fashion where kind of like around December, around April, searches for null hypothesis peak, and it's right around final exam times in university. And you see the same kind of trend happening with p-values. P-values are, I guess, a little bit less popular than the null hypothesis, but most of the searches for p-values are happening at these two specific times of year. Histogram, same kind of thing. People's searches for histograms look like they spike around the beginning of the school term in September, and then they kind of spike again around exam time. Here's another example of a line graph. This is page loads on our old learning management system, CU Learn, for students in this course. And so when we used to run this course in person, students would come to the lecture and they would get the assignment on the day of the lecture, and the assignment would be due the next day at midnight. And so they could work on the assignment during a period of about half an hour in lecture when we were all together in groups. They would work together, and then it wouldn't be due that night, it would be due the next day. And so if you went on and got the data for activity, students loading pages on CU Learn, you could see activity really spiked during the lecture, and then it would go quiet overnight, but then it would spike again. Students really liked doing the work in the kind of hour before the deadline. Okay, the last type of graph that we are going to look at in this lecture is a map. And a map is a way, it's the spatial equivalent of a line graph. And so instead of plotting the relationship between some variable and time, in a map we're plotting the relationship between some variable and space. Okay, so I have a couple of quick examples. This first one is a map of carbon dioxide emissions in metric tons per capita around the world. So each country has a single value of how much carbon dioxide is emitted per person. And the darker that country is shown, the higher the value of carbon dioxide emissions per person. And you can see the legend on the lower left that shows you what each of those shaded levels of shading actually mean in numbers. Here's another example of a map. You can check it out yourself online. Maps showing light pollution at night, so artificial light at night across the United States. And this comes from data from satellite imagery. And it's really neat because we have historic examples. So we can see, okay, how much light was there at night across the United States in the 1950s, and then we can look at that compared to the late 1990s and see how much more artificial light was being produced. Okay, so a summary slide here, and then we'll go into a little bit of practice. So, so this just lays out, okay, what you might be wanting to do and what type of data you have, and then the type of graph or visualization that you could use. Okay, so if you're interested to look at more, there's a couple of communities online where people share examples of really interesting graphs and also examples of really terrible graphs. I find it really interesting to go and look at some of these examples. They don't always agree with everything that people are posting. You know, sometimes people post things in the beautiful community that are actually mostly confusing, but it's really interesting to see how many more types of visualization there are than these simple ones. Oops, I went too far there. Okay, a few practice questions, and we'll take these up on Zoom. First of all, just what type of table is this out of the three types that we covered? This is data from a research paper. I think it was a study of reading, and yeah, so what type of table is that? Okay, second, we've got some information here on men's 100-meter world record race times over history. What type of graph is this? And third, here's an example of men's 100-meter race times again. These are personal bests for some of the fastest men in the world as of June 2019. So I think there's been some like records broken since then, probably for some of these people. But is this a good way to visualize this information? So we've got different athletes along the horizontal. We've got their times running the 100-meter along the vertical. Could we do better than this? So a problem here is that it doesn't really show us the difference between these athletes. And one solution is that we don't actually have to use a bar graph for this. So think about how we could represent these data in some other way. Okay, and the last slide for this lecture. One thing you should do now that you've watched this is go to Brightspace, get this PDF that I've posted called Biology 1105 Types of Graph Summary, and fill it in. Okay, so it's kind of a study aid. It shows you different types of data, and it asks you to kind of fill in the type of graph that would achieve different goals, and you should be able to fill that in based on this lecture. Okay, bye-bye.